Linear relationships. We're looking at points of intersection in this video. A point of intersection is the point where two lines meet. Now the x and y values of a point of intersection satisfy both equations at the same time. The equations of both lines at the very same time. A special sort of event here. So we've got a line there, y equals 2x minus 1, and we have another line there, y equals minus a half x plus 4, and you can see that there's a point of intersection. Can you see what coordinates that might have, what x and y values that might have, that point of intersection? Well, I'm here to tell you that has a point of 2, 3. It's got an x value of 2 and a y value of 3, and that's a very special point for these two lines. It's the point where these two lines meet. So we're going to explore those two equations of those lines and the point 2, 3 and see what's special about them if we substituted in the x value of 2 and a y value of 3 into each of those two lines. I'll show you what special thing mathematically occurs. Okay, so let's see how that point of intersection, the x and y values of that point, satisfy the equations of both lines at the same time. It's almost like we're showing that. We're going to show that the point 2, 3 lies on this left-hand line and the right-hand line at the same time. Okay, so that x value of the point is 2 and the y value is 3. So here I've substituted in, I've replaced the y with a 3 because my y value is 3, and 2 lots of whatever x is. So in red I've replaced the x with a 2, and let's see how that pans out. 2 times 2 in this section here is 4, so 3 is on the left hand side, and on the right hand side we have 4 minus 1. So I think you can see that'll simplify quite nicely to show that 3 equals 3. Now that has shown that those values of x equals 2 and y equals 3 have made the equation work properly. Or another way of saying it, they've satisfied the equation. They've made the left hand side of the equation equal the right hand side. Okay, let's have a look at the right hand equation here. Y equals minus a half x plus 4. Here I've substituted I've replaced my y with a 3, a bit like I did on the left hand side, and my x with a 2. In between here there's a multiply. Minus a half lots of 2. Now a half of 2 is 1. A minus times a plus makes a minus answer. So for that section there we will get a minus 1 for that chunk there. On the left hand side we have a 3. On the right hand side we have a minus 1 to be combined with a plus 4. So once again that works out really nicely. 3 equals 3 is the result of me subbing in x and y from the point into the equation, and that's made the left hand side equal the right hand side as well. So what have we shown there? Well, we've substituted the x and the y value from the point into each of the two equations, and in both cases they've made mathematical sense. We've got 3 equals 3 here, which makes a lot of sense, and 3 equals 3 was the simplified version of the right hand side. So what does that mean for us then? Well, what we've done is we've shown that the x and y values of that point have made both linear equations work properly. They've made the left hand side equal the right hand side in both cases. Another way of saying that is that we've really shown that the point 2, 3 is the point of intersection of y equals 2x minus 1 and y equals a minus a half x plus 4. Those were two lines, and that point 2, 3 was special in both cases. That point lay on both lines at the same time. It satisfied both equations. Both visually you could see that they crossed each other at 2, 3, but we've shown using algebra that that point worked beautifully with both equations of the lines at once. Okay, that's exploring points of intersection. I'll see you next time, but for any of your maths needs, peterblakemaths.com. Check it all out. See you next time. Bye.